So we will continue our discussion on the science assessment criteria, and for this video, we will focus on Criterion C, processing and evaluating. Here, we already assume that you have collected data, so the point of Criterion C is for you to organize it, present it in visual and numerical forms, and then draw information that can inform you of whether your initial prediction is correct or not, and also whether your method is actually valid or not. When you think about the word raw, we think of something that is fresh, something that you just got from the market. Raw meat, raw vegetable, raw fish, and raw everything. That's something that you cannot eat. You need to break that, you need to cut that into pieces, you need to add ingredients, you need to cook it in order for you to be able to take it in. In the same way, raw in terms of data is something that is just too much. It shows too many numbers and too many things. What you want to do with raw data is to simplify it into processed data. Instead of showing all the trials, averages, and all collected data, you may want to focus only on the simplified version of it. Show what actually matters and show new units in order to make sense of what you got. In this raw data, in order to simplify this, you may want to ignore all those trials and all those other numbers. You may want to focus on these averages. From these averages, we can now begin to have a better understanding of what happened. What is the difference before the candy and after the candy? You can now add a mathematical equation here, such as just simple subtraction or any equation that you need or you find necessary. From here, it would be easier for you to make a graph. But how do you make or how do you represent this into a graph? To choose the right kind of graph, you have to understand what is the kind of data that you are dealing with. Here we have what we call as nominal data, and we also have here numerical data. If you don't understand this, it would be important for you to have a look first at what are the different kinds of data. By definition, data is a plural word that is the plural version of datum. IB, United Nations, National Geographic, and even Wikipedia defines data as something that you collect, something that you analyze, and something that you organize in order to come up with a conclusion that it will inform your decision. We can also categorize data based on those sources into qualitative and quantitative. Qualitative means it's an information about the quality or characteristic. And for quantitative, it is indeed quantity or amount. We can also call the qualitative data in as a categorical data. It may refer to your religion, to your favorite car, or to your birth sex, something that you can choose from. So those are categories. We can divide them, this data, into nominal and ordinal. When you say nominal, these are just random named categories. Options such as insects or mammals or reptiles. It can be your names. It can be green, black, or blue, eye colors, or kinds of fruits. Ordinal, on the other hand, is a category that you can put in order or arrangement, such as small, medium, large, strongly agree, partially agree, or yes, maybe, no. This is the difference between them, but in any case, they are not referring to quantities. Numbers can still be considered categorical if it refers to arrangement or just a label, such as first, second, or third, but not necessarily defining a number in terms of measurement. When we talk about quantitative data, this obviously talks about numbers. This refers to quantities. We also call this as numerical data. We can divide that into discrete or continuous. Discrete numerical data only refers to measurements that have specific numbers or specific values, such as you were asked, how many siblings do you have, or how many countries have you been to? Your response to these questions are usually whole numbers, 1, 2, 3, 4, and a specific number that cannot be less than or in between any of those choices. On the other hand, when you talk about continuous numerical data, here any value is possible because here the numbers and the options are limitless. Say, for example, what's the concentration of a particular compound, or the concentration of carbon dioxide in air? How much is the distance between point A and point B? And here you can have multiple decimals, and there are just limitless possible answers in these data. When you understand the difference between nominal, ordinal, discrete, and continuous data, it can easily help you in identifying the kind of graph that you can use in your experiments. For simplicity, we are just going to discuss four different kinds of graphs. We can have more and we can approach it in different ways, but I will just stick to these four options. The first one is the pie chart, and the pie chart is simply showing parts of a whole. So you know the total, you know the parts, you know their values, you just convert it into percentage, and then you plug it in to your Excel to show you the pie chart. Example here would be the preferred devices of students, and you have here numbers of users and then the total. So you just divide these individual data into by the total and then multiply it by 100. That gives you a percentage. The second one is the bar graph, and the bar graph is very useful whenever we have a nominal data and numerical data. So say for example, we have here four different qualities, like what is the different colors of the candles that you are testing, and then how long will it take for them to melt. So there is a numerical data here, and then there is a um, nominal data here. The problem with this graph though is it's not complete. There is no title here, no axis label, no axis label. So this is not a very good graph yet. So there are two units here too, minutes and seconds. You don't want to put here minutes and seconds. Instead, you want to put here just time of melting in seconds. So you cannot use two different units here. Another way of using a bar graph would be having a paired bar graph, wherein you are having here one nominal data and then two numerical data, and then those two numerical data will be associated with that nominal data. So we have the name and the number, name, number. So that's going to be an example of how to use a bar graph. The third one is what we call as a line graph, and the line graph is very useful in showing one piece of data or one source of data that changes over time, like amount of sales over the course of the year, or the population over the year or years. And an example of that would be the population of deer in a given habitat, wherein its numbers will increase and decrease depending on other factors. So here you can see that there is a huge drop, and then it slowly increases again. Sometimes you can have a complex line graph just like this one, wherein you are looking at the population of deer and the population of fox to indicate, a predator-prey relationship. And you can see here that the number of deers are dropping, and as they drop, there will be an increase in the population of the fox until they don't have enough food. So that's how you can use it. Again, problem here, no title, no axis labels, but I will show you later an example of a graph with complete labels. We are now done with pie, bar, and line graph. The fourth one will be your scatter graph, and the scatter graph is very useful whenever we are showing not a nominal data, not time, but we have here quantity versus quantity. So two numerical data that is paired well together. What do you mean by paired well together? Going back to the data that I showed you a while ago, we have here different rays, and this is your nominal data. And then they have two different numerical data. But those two numerical data, we are trying to show that there is a correlation or a relationship or a connection between them. Say, for example, for East Asian men, average height will be 164. And if you are not very tall, obviously, it also follows that your weight is going to be very light. However, if we're going to talk about this data here, which is 177 Caucasian white men, they are usually the tallest, but at the same time, they are the heaviest. So we can now begin to draw a line that shows, oh, there is an increase An increase in the height would mean an increase in the weight. So this is now an example of a complete graph. You have a title, you have an axis label, y-axis label, and then the x-axis label, and then there will be a relationship between them. We can also label these dots. This is the East Asian by average, and this is going to be the Caucasian white male by average. Not saying that there aren't any white male that is not very tall and not very heavy, and not saying too that there are East Asian men that are not tall and not heavy. So these are the four kinds of graphs. What we have to remember is that they are useful in specific situations and they are not useful in all kinds of situations. Just remember that when you want to use pie graph, it's very useful for comparing parts of a whole. Bar graph is very useful when you have a numerical data associated with nominal data. Line graph is when you have one source of data that changes over time, so number versus time. And lastly is when you want to show some relationship between two numerical data, that's going to be the scatter graph. Going back then, we have here this process data a while ago, and this process data shows nominal data and numerical data. We even added that in processing your data, we have to add some mathematical equations such as a simple subtraction, just to show if there is an increase or decrease in the reaction time, if it got faster or slower. Here, it's obvious that we have a nominal versus numerical, so a bar graph is an important tool or an important representation that you can choose for this result. However, another layer of processing your data is not just choosing the correct graph. It's also important that we use the correct units. We want to show reaction time, we should show time. The unit for time is seconds, not centimeters. This centimeters is only representative of the tool that you use, which is the ruler. So you caught the ruler quite quickly, so from 0 to 15, that's a quick catch. You caught the ruler at mark 28, 0 to 28, that's not a very fast reaction. But then you want to convert that into time. So there are ways on how you can do that. So if you caught it at 15 point mark, then your reaction time is 179 of a millisecond. But if you caught it at 28, then your reaction time is a little bit slower. But how do you get that? There are two ways. Number one, you can do it manually. You can search up how to compute for the unit of time if you drop an object, and then you can add here a diagram too. There is the unit of time, then the distance by the ruler, and then the gravity is constant. And then you can give a sample calculation. Sample calculations are very important for Criterion C. The simpler way, in my opinion, would be just to search for some tools that can convert the centimeter, the point where you caught the ruler, to your reaction time. Or maybe just get a tool that can measure you the reaction time online, and then you just have to cite your sources or your tools. So now that we have shown the time and we have also chosen the correct graph, the next layer of processing your data will also include protecting the identity of your subjects like your volunteers. If you don't want their identity to be shown in your paper or in your experiment, you may want to cover them. Okay, so 1, 2, 3, 4, 5. And lastly, another layer of processing your data is asking yourself, is it important that I compare student 1 to 2 to 3 to 4? Is it important that I compare their before and after? Or do I just focus on the change? Or maybe I don't have to focus on individual students. Maybe I just have to focus on the class average. And if the answer is the class average is the only important thing to you, then you can hide all those data and just focus on this. Plus, you don't have to show the centimeters anymore, just show this. And from this simplified process data, you can now begin to have a more simple graph, which can now answer your question. Was your hypothesis correct? Or was your hypothesis supported? Or was it rejected? It's very important, Criterion C, that you turn your raw data into a processed data. But the other part of it is writing, writing what you saw. So here you may have chosen the correct graph, you may have labeled all the parts of it, but then you are going to describe it. And some guide questions that you can use are the following. Are all the data consistent? Are all the trials precise or repeatable? Were your expected numbers met? Was there a general trend? Are there confusing results? If the method is repeated, do we expect the same numbers to come out? Sometimes you will have to use some sentence starters like, from this graph, our group observed that majority of the participants had. Then you will follow it up with what did you observe or what did you see? Okay, so with the exception of two individuals, everyone had a faster reaction time. And after you say your sentence starter and your observation, you end it with your peculiarities or possible explanation. When you say peculiarities, it means what are some things here that I don't really expect to happen? Okay, or what's one thing that is not really following the group? So it is possible that their reaction time, say for example, um, some of them, it's possible that their reaction time is an unintended effect of observing other people's performance. Maybe Hinoa is one of the last people to do the test, and she have seen everyone, and so she wanted to do her best. So it's probably not because of your independent variable, which is the candy. It's probably because of something else. So that's a possible explanation. I'm not saying that that is the explanation, but you've got to give your view of your data. Another way of checking whether your data is precise, is it repeatable, is to take a look at sometimes not the process data, but sometimes you have to go back with your raw data. So here we have some highlighted numbers, the before and after numbers of Marie, the before and after numbers of Yuma and Shion. And if we are going to look at these numbers, if you only look at the average, you will say, oh, the average is 27 and 22 and 19 and 17. And so Marie would have a lower reaction time compared to Yuma, and Shion would have a higher reaction time than everyone else. Then you are going to be missing out on some important numbers, like this 14. At one point, Marie had the fastest reaction time of everyone. So how do we now describe and how do we analyze these numbers? You have to take a look at the average. So you now compare that average to the maximum number within that sample data. So 27, the highest number is 41. There is a huge difference there. So that's going to be the highest point is higher by 14 compared to the average. The highest point compared to the average is 8.3. That's a huge margin. That's a huge gap with the average. Whereas for Yuma, it's only a difference of 1. The average is 19, the highest number is 20. For Shion, the average is 17.3, the highest is 18. So this one, they are now the upper group or the upper number. How about if we compare the average to the minimum? 27 and 18 would have a difference of minus 8. 22.7 and 14 would have a difference of 8.7. And then 1, and then negative 1.3 or minus 1.3. We will now have to represent this in some way. You will now copy your 27, and then you will choose the bigger number here. And the range here is going to be plus minus 14. What it means is that if you repeat this experiment, we can expect that Marie can have a number, can have a reaction time of 27 more or less by 14. So 27 up to 41, 27 up to maybe 10. So that's going to be your expected number. The higher is your range of uncertainty, the less precise is your data. It's not very trustworthy. It's not a very good measurement. It means to say that anything can go wrong here. And there are so many factors in play. Why sometimes he reacts slowly or she reacts slowly, and sometimes she reacts quickly. So these are not very good measurements, and you will now have to describe that. What are the possible sources of error? What could those causes of errors be? So maybe someone was telling a joke, maybe someone was distracting her, maybe there are some discomfort happening. That's why she didn't give you a very consistent number. Whereas for Yuma and for Shion, you can expect that they were very, very focused on the test. From here, you will now end your experiment with describing all of your findings, all of your doubts, and all of your possible explanation, and what are the things that you can do to change your experiment to improve it. And that should be it. It's supposed to be fun, and it's supposed to be a good assessment to do because it exercises your creativity and your critical thinking. So that's going to be it for your Criterion C, processing and evaluating.